Good morning. My name is Jakub Pluta. I'm from ISNAP, Polish SME, and dissemination partner of the CIRMET project. Welcome everyone to the third webinar of the CIRMET project, focusing on the analytics for factories 4.0. The presentations will start with Michael Merchant from TECNALIA, the coordination partner of the CIRMET project, who presents the overview of the project. Then Joseba Egia from MSI Group will present short the challenges and barriers for implementation of digital systems in industries. And after this, Fernando Botto and Joseba Egia will present the brief introduction of the today's presented technology from the CIRMET project. After this, Mayalen Murua from TECNALIA will present the soft sensor development in EAF process. And after this, again, Fernando Botto and Joseba Egia will present the results exploitation to the market. And after this presentation, they will give the real-time demonstration of the platform. At the end of the webinar, we will have the question and answer session. In your control panel, you can see the question mark where you can put your questions, and then at the end we will try to answer all of them. Also, I would like to point that this webinar will be recorded, and soon it will be published in our website and YouTube channel. So now I would like to give the floor to Michael Merchant to present the overview of the CIRMET project.
Okay, thank you, Jakub, for the introduction. Good morning, everyone, and thank you for attending this third and last of the series of webinars. I'd like to present the technologies that are being developed within the European-funded CIRMET project. My name is Michael Merchant. I am a senior researcher at TECNALIA, and I am also part of the team in TECNALIA that, together with Maider García Cortázar and Guadalupe Lobo, is in charge of the coordination activities of this project. In this first presentation, I'm going to briefly show an overview of what the project consortium is developing. CIRMET is an European-funded project. It is funded by the European Union 2020 Research and Innovation Program under this grant agreement. It has a duration of 4 years, and the ending is foreseen by the end of September this year. It has a budget of close to 10 million euros. And 15 partners from 6 different European countries with complementary profiles are part of this consortium. The main objective of the CIRMET project is to design, to develop, and to validate at a relevant operational environment a solution to provide energy and resource flexibility to the energy-intensive industries. The project addresses some of the challenges of the industrial sectors which are considered as process industries. Some examples are cement plants, are also steel-making companies, and non-ferrous industries. These 3 industries are represented by 3 different companies that have the role of possible end users of the technologies in this project. Processing industries are characterized, on the one hand, because they have a very high consumption of raw materials, because they need to use these raw materials because they have to extract, to transport, and to process these raw materials to manufacture semi-finished or high-quality end products. And they are also high consumers of energy, because this manufacture is carried out by means of physical, mechanical, or chemical processes, which of course consume a lot of energy. Some of the challenges of the European process industries are facing nowadays are the following. The first one is try to reduce the dependency from third countries. In the case of raw materials, as you probably know, some of these materials have been already catalogued as critical raw materials by the European Commission, because it can be that they are only obtained in third countries outside from Europe, or it can be also because their shortage. So there is a need to increase the recycling rate of these materials. And in the case of energy, I think we currently are all aware of the consequences of this dependency. The second challenge is to try to increase the energy efficiency of the process unit operations. This way, we can reduce the overall energy consumption of the processes, and this can have a positive impact not only on the environment, of course, but also in the competitiveness of the European companies. The third challenge is the adaptation of the production processes to the increasingly sustainable but highly fluctuating energy supplies. This is related mainly to the increasing share of renewable energies in the energy mix, which means that we can have a fluctuating availability of energy in the future, and this can mean that we need to adapt the consumption of energy of the industrial processes to this new scenario that is. The next challenge is, of course, try to reduce the fossil-based CO2 emissions, and this is mainly related to the fight with the climate change, and try to reach this climate neutrality by 2050. That is one of the main objectives of the European Union. And finally, and of course related to some of the previous challenges, then last one is try to increase the competitiveness of the European process industry so they can compete with the emerging countries. Okay, most of these challenges have been considered in the design of what we call the CIRMET solution. Schematically shown, the solution can be considered as a process unit, this one, that can be integrated in an already existing process unit. The current process unit uses some raw material to produce, using energy, of course, some products, but also some byproducts and wastes. The idea is to take these byproducts and wastes, introduce them in CIRMET, and thanks to a valorization process, obtain a revalorized byproduct that can have a higher value in the market, and also obtain some inner waste or inner slag that can also find an application in the market. So we avoid any way to be landfilled. At the same time, some materials can be recovered and eventually introduced again in the process unit, thus reducing the overall consumption of primary raw material needed. And finally, we can also recover some heat from waste gases and transforming this heat into another kind of useful energy, introduce this or use this energy again in the process unit or in the plant, so the overall consumption of energy is reduced, and this also have a consequence in as a consequence, this reduce the CO2 emissions. So we can say that this solution can have an impact in the reduction of primary raw material consumption, in the increase of the energy efficiency of the process, in the reduction of the fossil-based CO2 emissions, and in the reduction of the production cost. This solution is a modular solution that is integrated by a metallurgical furnace, an energy recovery device, and a digital platform. The first of the modules, the one that was presented in the first webinar, is the EFIMELT metallurgical furnace. This is an innovative metallurgical furnace which is based on a high-power thermoplasma energy system, which has high efficiency, and also uses biogenic carbon coming from biomass to recover metals from industrial waste. The second of the modules, the one that was presented in the second session of the series of webinars, is the record waste heat recovery and storage unit. This unit takes waste heat from flue gases and transforms it into compressed air using an ORC unit, and it gives the possibility of adapting the energy generated to the compressed air demanded through a continuous variable transmission system and also with an energy storage system. These two webinars, as explained by Jakub, were recorded and are already available in CIRMET's project webpage and also in our YouTube channel in case you want to watch it. And the third of the modules, the one that will be presented today, is the Analytic for Factories 4.0 digital platform. That is a platform that is composed by different physical and digital tools that are able to acquire and monitor process parameters and are also able to predict and optimize the parameters of the industrial process, as it will be shown along the webinar. I would like to take advantage of this slide to thank all of you for your attention, but also to thank all the 15 partners, the project consortium, due to their work and commitment along the duration of the project. And these are my contact details. Of course, I will be ready to answer your questions at the end of the session. But if you have any other question and you want to contact me to have more information on the project, of course, you can use my email. Thank you.
Thank you very much, Mikel. Now I would like to give the floor to Joseba Egia, who will present the barriers and challenges that still has to be faced in implementation of digital system in industries. So, Joseba, the floor is yours.
Thank you, Jakub. Okay, so my name is Joseba Egia, as Jakub said, and I'm a manufacturing analytic consultant on MSI. And I'm going to tell you about the challenges and barriers of digital system of data analysis in industries. So, when we talk about an industrial data digital system, we usually think only about data visualization or artificial intelligence models, but this is just the type of iceberg. The natural step of the organizations are made by this natural step of each organization are made different ways and different types. The approach to a big data or artificial intelligence systems. But the thing is that the first step are mainly technical of connectivity, processing data, and connecting to the different operational information on layer systems. And then we have to focus on transformation of the data and interpretation of this data to help the decision making. And this can be done by the visual data or also by artificial intelligence. So first of all, we have to take the data and then we can treat it to create information, valuable information. So well, I think with this picture you can understand it better, and you can put the cart before the horse. We need a very good data to create artificial intelligence models, but also to create a visual data that is useful to take decisions. Whatever the data decision driver system is, human, hybrid, or artificial intelligence, if you have correct data, it means that you are not going to take correct decisions. And when I say correct data, I mean not only a lot of data, because in artificial intelligence models, we usually think about a big data or big databases. It means that we need validated, enriched, and monitored data. And this is something that we have to keep in mind. Okay, so the 4 keys to ensure that the decision making is not biased by using, as I said, unvalidated or unrepresentative data or altered data are these 4 keys that are capturing the information on source at a smart way. Okay, we have to monitor the capture frequencies that we expect, and then we have to validate. And the second key is to validate and treat the data and transform to enriched data. And therefore, we have to go to have the valuable information. The next key is storage the data in a correct way. We need different storage types for each kind of data that we are going to have. And the access has to be fast and reliable, but most important, I think, it has to be secure. Okay, the cyber secure. Okay, and the last key, the subsequent exploitation of the information for a good decision making, as I say. The data analytics is not just creating a bunch of charts with no relation between them and put a lot of data in a visual data dashboards. We need a comprehensive dashboards for humans, and also if we are going to use this data in artificial intelligence models or to train these kind of models, we need to prepare the data for the way that artificial intelligence model needs to fit it to train it. Okay. Sorry. So now with these principles in mind, I think that we are going to see the different challenges of the different parts of the way of taking data and transforming into information. The first part is, as I said, the data acquisition challenges that are the first one that we are going to face. These ones are, I think, most commonly known because I think a lot of companies have started acquiring data, but they are not trading it in the way that it is transformed to a valuable information. But in acquisition challenges are interoperability issues between the protocols that we used to use in operation layer and information layers, the unavailability of the communication infrastructure that maybe people of operational is not used to not to have communications availability, complexity to obtain the data in the expected frequencies that I told you. Sometimes we have different origins of data with different capture frequencies, and putting all together is quite complicated or can be complicated. Also, low bandwidth for raw data uploading. This is more related to when we have remote locations and we are using cellular data to upload the data. Then high volume of data to just high frequency that maybe if we are using edge devices that later we are going to see, the capabilities of this kind of PCs or small PCs are can be not enough to ingest all the high volume data in real time. And one of the things that we are going to see in this presentation are this vulnerability of the context data. And then, as I said, the security of the transport layer and storage. Okay, so how to deal with these challenges is just an approach, but point by point, I think that the first of all is always try to obtain data from no time source. In industrial protocols are a lot of different kinds. There are some standards protocols that are taking place in the industry, such as OPC1, that it's known for everybody, and it can be secure, and I think it's more or less a standard. So using this kind of source type of data is going to be the easiest way to achieve a good capture of data. Then use ACKs or buffers. If in case that we lose communication with the transportation layer or storage layer, we have to buffer the data, and then with the connection established, we can upload the data In this way, we are not going to lose anything. And for artificial intelligence models, it's very important to have a complete data sets. Then the reduction of the data sets using aggregate such as mean, max, mean, standard deviation, that sometimes in the origin of the data, or the source of the data, we are going to have a high rate of data that we really don't need. So aggregating the data to have a lower resolution, it can be better for storage, and also it's usually enough to have good information. Then apply a validity rate to disaggregated data. When we do mean or max or standard deviation calculations, we have to be sure that we are doing calculation with real data. Okay, so if we are using data that is not reliable, we are losing points of data in the time that we are doing the calculation. For example, 10 minutes mean values. If you are only having data for 5 minutes, we have to know that this data can be biased because it's not really showing us what happened in the process. So as you can see, we can use calculation of validity rate, and then when we are going to take decision, we have to be aware of what validity rate has our data. Scalability of the hardware and software. Using more powerful hardware and software is going to be always better if we have a lot of data. And then to have context data, use wireless sensor connectivity with IT protocols such as MOM, RP systems to have to know what is happening, not only the process data, to have a context data, and then communication has to be encrypted and with no trust. Okay. So the challenges of transforming the information to the data to information are usually the first one is data is not being monitored. Typical case that a company have been capturing data for 3 years, but nobody has been looking for this data. So we don't really know how good is this data and how real is this data. So the first step is monitor this data and validate that the values that we are adhering are correct. Then define or not define representative mistolerances of the data. Next point is different scale of different units of measurement for the same types of data. Is quite common that we have 2 sources of theoretically the same data type, that we have different units of measurements. Again, lack of context data, low validity rates in the aggregated data. And then we have to keep in mind that any change of operations layer, if we change a machine or we change a sensor or we change operability system, it's going to affect the data, and therefore it's going to affect to the visual data dashboard that we have created, or the AI models that we are using to use as a decision support system, and also too much data and visual analytics. So how to deal with these problems? As I say, monitor the data pipelines, use simple rate validation. We have to define the tolerances of the different values on the different points of the time of the process using context data that we need. Again, standardize the units of measurement of all the sensor or all the process point that we are measuring. Again, add as much context as possible, because it's going to be the key to know what is happening and if the data that we are acquiring is correct or is not correct. And then, as I say, operational changes must be taken into account. Simple dashboard, simple. Okay, and for the last challenges that we have regarding to visual analytics are, as in this example, we can see, I don't know if you can see which are the most important KPIs in these dashboards. I can't, really I can't. So this is example to how not to do a visual analytics. Humans are not good monitoring too many variables at the same time. For that, we have artificial intelligence models. So when we do visual data analytics, I think that we always have to try to simplify the dashboards, creating complex KPIs that are representative to the process, and for the things that we really want to monitor, and don't create this kind of mess that we don't really know what is happening and what is good and what is bad in the process in this real-time dashboard. And just to finish, I create this silly example of to understand why the context data is key when we acquire data from a process. That if we see this example just of car radar of a speed limit, and we have only the speed and the plate of the car, with this without context, in this case, both of the cars deserve a fine because they are over the speed limit. But if we add context to this information, that which kind of car is the one that has been taken the photo, we can see that maybe our decision of finding the two cars is not that correct as we think, because the car B, at least it can be possible, the situation, but the car A is not very suspicious to be false positives or something like this. So in this case, everyone is going to ask that the car A camera or radar is not reliable, but the things that we have to ask also as we are taking information with two kind of same data is, are both radars the same model? Because if these two radars are the same model, we are going to have some problems also in the car B. And if both of them are correctly calibrated, these kind of questions are important, not just focusing that car A scenario is not reliable. Okay, so I think with this, I finished this part. Thank you.
Okay, thank you, Joseba. So now I would like to ask you and also Fernando Boto from TECNALIA to present us the brief introduction of the analytics for the future.
Okay, thank you, Jakub. Okay, my name is Fernando Boto, and with Joseba, we will present this a brief introduction of AFF 4.0. I work in TECNALIA. I am a data scientist and artificial intelligence expert in industrial application and process optimization. In this presentation, we will introduce the analytics for factories 4.0 developed in CIRMET. The aim of this work is to develop scalable and adaptable monitoring, control, and data analytics tools to improve process plant competitiveness, maximize final product repeatability, and waste valorization. Increasing resource use efficiency, optimizing CIRMET process units, and all these merging different sources of information. The methodology in AFF 4.0 covers all the aspects related to a data-driven project. First of all, digitization, providing the instrumentation and control of new CIRMET equipment, that is eFilment and rocky waste. Descriptive analytics, providing easy to understand resource efficiency indicators, using information from different sources, and allowing quick decision process and identification of gap improvement. Then predictive analytics, providing real-time information of quality or performance related parameters, not available nowadays or difficult to measure. And finally, prescriptive analytics, providing operator support tools for the optimization control of process set points with economic and resource efficiency target. Okay. This is the schema for the AFF 4.0 platform, composed by some tools integrated in the virtual part and some other tools integrated in the physical part. And in the middle, a module of data fusion layer that is the link between both parts. When talking about industrial process, we are mainly talking about effing melt and recoup waste, explained in the first two webinars, but we have worked also with some other industries and in other vertical sectors in order to analyze the possibility of using these developments in different industries. We are doing so in a case of cementing rosin process in cement sector and in siderurgic and siderurgical sector, as will be explained in this webinar. In the green boxes, we can see the hardware and software modules developed. First of all, in the physical part, the monitoring and control tool, and in the virtual part, we can highlight the soft sensor developed, as well as the process prescriptive tools. Finally, the descriptive resource use tool that brings together the AFF 4.0 methodology in a user interface. This is the AFF 4.0 methodology we follow. The thing is that companies want to know what is happening now, what will happen in the future, and what are the course of actions they can take to reach an optimal result. These enterprises hold data and need to extract insights from this data to take advantage of future opportunities and decrease possible risks. So, according to the literature, business analytics is categorized mainly in three stages. First, descriptive analytics, which is the data summarization phase and reports the past. The answer, it answers to the question what has happened and why, and extracts information from that data. We are including here the diagnosis part. Then predictive analytics, which is the forecasting or extrapolation phase, and incorporates the descriptive analytics outputs, and as well as some machine learning algorithms and simulations techniques to build accurate models that predict the future. It answers the question, what will happen and why will it happen in the future? And finally, prescriptive analytics, which is the recommender or guidance phase, provides enterprises with adaptive, automated, time-dependent, and optimal decision. Its goal is to bring business value through better strategic and operational decisions. Now we are explaining how this is implemented in this strategy in CIRMET in AF 4.0.
Thank you, Fernando. So, as Fernando said, in the descriptive analytics tool, we like to look at what happened and why it's happening. And to this task, we like to divide the descriptive analytics into two different kind of visualization types and two kind of data visualization. Okay, so the first one is just descriptive analytics, that the aim is to see what happened in the past, and this past can be a minute ago or 5 years ago. So it's just a way to see real-time or historical data represented in time series visualization kind of charts, and also some kind of KPIs that we can monitor. And the idea of this descriptive analytics tool is to understand the process and try to minimize any problems in short term. Okay. But also in descriptive analytics, we like to add the diagnosis analytics kind of visualization, that this kind of visualization is not only based on time series data. This is mixed with structured data to have more information of the context that what happened in the past. So with all this information mixed, we can try to answer the question of why that happened in different moments of our process. So the idea is to look about the trends or correlation between variables, and also to try to answer the root case of the things that happened in the past. And then with all this information, try to take decisions in the future, or what kind of decision that we have to take to avoid this to happen again, or to achieve that kind of KPI again in the future.
Okay, now predictive analytics allows to model the behavior of the process or a part of the process, so future outcomes can be predicted or estimated. This capacity to see what will happen in the future will allow to inform the operator about the situation, which can be desired or undesired. The development of data-driven predictive model comprises a series of phases, and the most important being those related to the construction of historical data for the model. These are the identification of the objectives first, and understand the problem, collect and review the data, and very important, to pre-processing in order to clean and select the most important variables. So when we have this historical data, we have to build the model, we have to select the most suited and parametricized technique, and then the evaluation with the predictions quantifies the performance in relation with the objectives of the project. An example of a predictive analytics phase, or the application of this strategy, is a sub-sensor, what we call a sub-sensor. A sub-sensor is a predictive model, as I said, based on massive amounts of data, which are mainly responsible for online predictions of some variables that play an indispensable role in quality control of an industrial process. In CIRMET, we have implemented a sub-sensor in the electric arc furnace of Sidenor that will be explained later in this webinar. In the prescriptive analytics, finally, is to allowing to identify which process parameters or set points must be changed to reach the future resource efficiency target, as identified in the previous stage, the predictive stage. Due to the dynamic character of the process, the values of the set points can change over time and can be presented in a decision support system to the operator for review or applied directly to the automation of the process. In CIRMET, we have implemented a decision support strategy based on evolutionary algorithms, which use a regression model as a cost function, as you can see here in this part, and the evolutionary strategy is this loop we can see here. The strategy manages optimization configuration considering controllable and non-controllable variables of the process. This strategy is implemented in a web-based and easy-to-use application that will be shown later. The application we call EasyOpt.
Okay, so now how we implement all these that we have seen of data treatment is using a data fusion layer, as Fernando said in the scheme at the start of this part. We create a data flow upstream from process to exploitation using edge devices that are small PCs that we can put in operational layer of the technology network, and then we transfer and process data at the edge device inside the device, and then we transport it to information technology layer with a different protocol that is encrypted and secure. These edge devices are based on microservices architecture, so they can be scaled. They are scalable according to the specific need of each situation, of different processes, different data flows, and amount of data that they have to ingest. So just to have a small idea of what we do in edge devices, we use flow-based development tool called Node-RED to program visually the flows of data taken from operational technologies to informational technologies. This flow-based programming is doing the work of collecting, transforming, and send the factory data, operating data from any kind of industrial data source to the storage layer that is in the cloud. Okay. This communication between edge devices and cloud layers are secured by encrypted communication protocols such as MQTT or HTTPS, and this allows us to segmentate physically the layers of operational technology and information technology. And then the storage, as I said at the first part, is made according to the type of data that is being acquired. If it is time series, is going to be saved or stored in real time time series kind of database. If it is structured data, is going to be saved in structural databases. And then finally, we in this the data layer or the fusion layer, sorry, we made also a fusion layer regarding to the third-party applications such as the prescriptive or predictive analytical tool of TECNALIA called EasyOpt, and this is have been done using AP REST or MQTT communications. So in this way, we can give the ability or have the ability for the prescriptive technology application to extract the data that they need to train the model directly from the databases that are collecting the data for the operations. Then also they can write directly the output of their models or the decision support system in these databases, so we can use the visual data system and then we are going to see to show the operator what kind of the decisions they are proposing to put in the machine or in the process. So they are bidirectional, as I say. And also we made a embedded embedded tool of HTTP as a frame. So this can be launched, or the decision support system can be launched automatically using the API REST, but also it can be launched manually, so the operation manager can test different situations that are not have been seen, or they want to try a different mixture or different configuration of the line, of the machine, of the process to see what the decision support system will say that you have to do.
Okay, in the process optimization methodology implemented in CIRMET, it's very important to develop predictive models because they are the base of the soft sensing and the decision support system. That is to develop predictive models or the prescriptive. So in CIRMET, we develop a user interface to pre-process the data, to select the most important variables, to clean the data, and to make an easy evaluation of a model in an way where we can select the strategy, the strategy to model the data, to parameterize the model, but also we include a beginner mode where a process expert user can build its own models for the process. The result here is a web-based application where the expert user can build his or her own models for the process and evaluate them. And we developed also a prescriptive tool as a result of the evolutionary strategy. It's a decision support system. It's also a web-based application where an expert user can configure an optimization scenario and analyze the results. The application is a general approach, so this is replicable and flexible system where each industrial case is implemented very easily once we have the process models involved. We want to highlight that we can manage with this application a multi-objective optimization cases and different constraints scenarios defined by the user.
Okay, and to end this part of the presentation, this just a brief results of the dashboard analytics, visual analytics tool. This is a prototype that we have done with Cementi Rossi. This is a cement sector use case that we are working with, and this is a KPI monitoring dashboard that we can. You can see that there are different kind of visualization of different kind of data, and in the big KPI is the ratio of the energy usage against the production. And also, just to keep in mind that the visualization of complex data can be done in an easy way using here the map analytics tool that is a kind of a map of environmental experience of what's in the KPIs that you want to monitor. This part of the tool is you have the ability to zoom in and zoom out. It depends on the data that you want to see. If you want to see big KPIs of all over the world, you can just zoom out. But if you want to see complex data or data regarding to the process in one of the plants, you can zoom in, and the data is going to be more complex. And also, you can use some kind of filters to define what kind of data you want to see, process data or this kind of filters. So thank you.
Thank you very much for introducing the third CIRMET technology. Now I would like to give the floor to Mayalen Murua from TECNALIA to present the soft sensor development.
Yes, thank you, Jacob. Good morning to all. I am Mayalen Murua, data science researcher at TECNALIA, and I will present the soft sensor development in the electric arc furnace process. So the efficiency of industrial processes is of great importance, especially when it is intended to reduce the ecological footprint while maintaining the production availability. In the industrial sector and in some traditional industrial processes, such as the steel industry, more and more elements of the chain are digitized. So in this context, the optimization of the steel production tends to apply new technologies such as automation, digitalization, artificial intelligence, and so on, which will make these processes more efficient. So as my colleague Fernando already mentioned, a sub-sensor SS is an online tool that aims at online forecasting of certain variables that are important in the quality control of the process. So in some industrial processes, it's difficult to measure online some variables because there are technical or economic limitations. So in these cases, an SS paradigm is a good option because it provides a reliable and stable estimation. So the objective of this work was to control by a subsensor the quantity and the composition of the generated slag in an EAF process. The amount of slag is very important factor because it's an indicator of the efficiency of the process. So an estimation prior to the melting process is considered of great importance from an economic point of view. So I will give now some basic notions related to a process. The steel production can be divided into two phases, primary metallurgy and secondary metallurgy. So in primary metallurgy, the raw material that can be scrap or iron ore is converted into steel. During the secondary metallurgy, the alloy is refined and its chemical composition is adjusted. But in this work, we will focus on primary metallurgy only. So primary metallurgy is achieved across two main routes, and one of them is the electric arc furnace or EAF route. So in this case, the steel is produced using recycled steel, 100%, about 100%, and electricity. So only nowadays, only it's 28% of the steel produced by the EAF. But it's very relevant, and it will be very relevant in the future because it has major flexibility than the other route and sustainability. So the EAF process usually consists of a bottom vessel lined with refractory and is covered with openings for the electrodes. So the graphite electrodes, in this case we have three electrodes, are connected to the alternate current, and they create an electric arc between the strap and the arcs. So the furnace has different openings to extract the liquid steel, the generated slag, and to add also lime and to insert the lances for injection of oxygen, gas, or carbon. The scrap is inserted into enormous baskets in this case, and the part of additives are such as the lime are added in each basket, and the rest is added in the last stage together with the injection of oxygen, carbon, or gas. So the generated slack quantity forecasting is one of the most critical process parameter and should be under control. The slack is extracted from the furnace using a slack pot to be measured, and every casting the generated slack is removed from the furnace using that slack pot. Nevertheless, there is some quantity always remaining in the furnace. So here you can observe the predictive variables that we are going to consider in the analysis. So they are divided in different groups, and you can see the name of the group and how many variables we have in each of them. So in the variables of group other, we have the uses of the furnace bottom, the furnace shell ID, the presence or absence of the dyed origin blue, DPP, and the day of the week. The furnace bottom is repaired every 2 weeks, and once a month the furnace bottom is changed. So every time that the furnace bottom is changed, that variable is initialized to 0. Also, we have in this case 2 furnace shells, and sometimes DPPs are used to insert argon and to facilitate a chemical reaction. And this process is organized in cycles. One cycle corresponds to a week. So at the end of the week, the furnace is cleared out, so all the slag is removed from the furnace, and there is a time gap between the last casting of a cycle and the first casting of the next cycle. So we are going to address this problem of the prediction of the slag quantity as a regression task, where the regression is based on some predictive variables that were shown before to describe the EAF process. So this approach, machine learning based approach, consists first of applying data filtering techniques, and then selecting the predictive variables, and then building the predictive model. But we are going to use here 3 different focuses. So the first one is a weekly model of the generated slag, the second is the calculated slag model, and the third one is the slag composition model. So here we can see the data preprocessing. So this was focused on filtering some castings that were not suitable for the analysis. So on the one hand, this step of filtering was carried out with the help of an expert person with experience and knowledge about the EAF process. So the table shows the feasible ranges, values that are permitted to take for the variables. So we can see the minimum and the maximum values of those ranges. So the values that are out of the defined ranges are considered anomalies of the process and are not taken into account. On the other hand, the castings also were filtered using some statistical analysis. So this was done for variables of addition and injection models. So in this case, the minimum and maximum of the feasible ranges were defined by this formula, where mu is the mean value, sigma is the standard deviation, and d is a constant. In this case, d is equal to 2. So in the case of the addition, the minimum was always C. So to define the training and testing sets, we use different techniques depending on the scenario. So we have the k-fold cross-validation. In this case, the data set D is randomly split in k-subsets, approximately equal size. The sets are used for training and testing, k times. So at each time we use the k minus 1 to train, and the kth one we use for testing. Then we've got leaf-on-out cross-validation, that it's in a specific case of the k-fold cross-validation for k equal to n, where n is the number of observations. So regarding to the error metrics, we are going to use the mean absolute error, or MAE. It measures the average of absolute errors. And for better interpretability of the MAE, we are going to use also the normalized MAE. And we are going to use also the coefficient of determination, score, that is the proportion of variance in the target variable that is predictable for the input variables. So we are going to use different machine learning algorithms in this research. The methods, they belong to the family of ensemble learning techniques. So we are going to use random forest regressor that belongs to the ensemble learning methods. Combines here decision trees with the notion of an ensemble, and it belongs to the BiEMH family. So that is, it combines multiple regressors modeled on different subsamples in order to reduce the variance of the predictions. And we have the gradient boosting regressor, also belonging to the family of ensemble learning techniques, but in this case, this is a boosting algorithm, so it uses weak regressors in a different way. So now we are going to go to the models. So in the case of the weekly model, here you can see we have 42 predictive variables and 26 casting samples, in this case weeks. So here you can see the predictive variables that we used and the target employed. So in this case, we added all the variables weekly, and in the case of the furnace shell, all the castings were done in the same furnace shell, so it was not a problem. In the case of the uses of the floor, the maximum was considered, and here we can see the results. We used a random forest method in this case with the leave one out cross validation, and you can see there the obtained error, taking into account that that's weekly estimation, so the quantities are quite big. But we also estimate the MAE per casting, taking into account the average number of castings per week. So this we did with a measured quantity of the slag, because remember that at the end of the week the furnace is cleared out, so this value it's reliable. Then to do a model but per casting, we used the simulated slag in this case. So this was calculated using a mass balance modeling focused in the lime. So in this case, we used these variables. So the model was trained with 387 castings and 45 variables. Here we have a reduced set of castings, because not for all the castings the composition of the slag was performed. In this case, we employed the gradient boosting regressor with 5-fold cross validation, and you can see there the error obtained, the MAE, and also the coefficient of determination. And finally, here we have the composition, the different composition of the slag, the lime percentage, and the silicon oxide percentage. Here we used the same number of castings and as the previous case, and also 45 variables. And in this case, we used also the random forest regressor and the 5-fold cross validation. So here you can see for the two methods, the MAE and the determination coefficient of the two models. And finally, we are going to compare all the models that we obtained. So the problem of predicting the quantity of the slag was quite challenging, because the data was not reliable at all, because some slag also was always was remaining in the furnace, and also the complexity of the process itself. So here you've got the normalized MAE values for all the methods. So we can see that the lowest value was achieved for the simulated slag model, continues with the lime percentage, and the worst was for the weekly model and for the silicon oxide percentage. So these relatively modest results were obtained in the case of the weekly model. We think that it's because the low quantity of weeks that we have, only 26. And then we have to take into account that data-driven models with simulated data, they perform better than models fitted with real data. So that explains that the lowest error was obtained for the simulated SLAG model. And finally, I will mention some conclusions obtained from this work. So we used different approaches to deal with the SLAG prediction problem. The problem was challenging, as I mentioned, because of non-reliability of the data and the complexity of the EAF process. And the best results were obtained for the SLAG simulated model, achieving lowest normalized MAE. And the only way to consider the measured SLAG was doing weekly, because, as I mentioned, the generated SLAG it's not removed at the end of casting. So thank you very much for your attention. You can, if you have any question, you can ask me later. And here you can see my contact details.
Thank you, Mayalen. So now I would like to ask Fernando and Joseba to present us the results of exploitation to the market for this technology. So Fernando, Joseba, the floor is yours.
Thank you, Jacob. So the first thing that I want to mention is that the platform that we have been talking about data analytics is the AFF 4.0. It has been transformed into a product that we are now commercializing that is called Manufacturing Analytics. We have created a website that where we explain all the technology and the challenges of data that I have been explaining in this presentation. So I invite you to go to visit the web page and explore all the information that we have put in this web page. Okay, regarding to the use at the validation or replication phase of the platform, we are already using the integration on the request demonstrator, which you can see at the top of the screen. Also, we integrated in this demonstrator connection with integrated web page of Wireless Value, that is one of the partners of the project, that is placing some wireless sensors in the demonstrator. And in the lower part of the at right, you can see a small demo that we are using, or we have created regarding to the work package 6 that is going to be integrated also with the result of the artificial intelligence model that we are going to use in this part of the project. Also, in the replication, regarding to the replication, we are in progress of a water use case, specifically it's a wastewater sector. Here you can see some dashboards related to monitor the energy efficiency of aeration process. That is the elimination of VOT on COT against the consumed electricity, which is a higher energy demanding process in the cleaning the water, the wastewater. Then here you can see the exploitation to the market examples. This is regarding to real clients in the real world that we are already implementing the platform with them. Actually, we are implementing the manufacturing analytics platform with more than 5 clients of different sectors: glass, wastewater, as I say, gas burner safety parts manufacturing, electrical heaters manufacturing, and furniture manufacturing. So as you can see, it's not only related to big industries as steel or cement. We can implement this technology or these tools in any kind of manufacturing processes. At the top part, you can see a Sankey kind of visualization that is very useful to learn how your energy consumption is distributed through the plant. And the second one, at the low part at the bottom, is a decision support system of glass bottle annealing furnace. As you can see at the top part, you have the different variables that we are reading, and in white, the target of the decision support system that you have to implement if you want to be in the optimal configuration for this kind of production. And also here, the different burners or gas burners of the furnace with the temperature. And also regarding to the lean manufacturing, or the second part of analytical data of a process, one is just to consume less, but also a good way to consume less is to produce better, or with less scrap, or with less bad parts. So these two visualizations are classical monitoring analyzing dashboards. The top of one is a real-time dashboard of OEE that you can see or monitor the evolution shift by shift. And the second one at the bottom is a more advanced analytic tool where the context data of the production, such as lines, product, shift, or operations that are taken into account as filters, so you can do some kind of benchmarking of the different points of the production, different moments of the production, or different lines, or different operator groups, or different shifts, to take information about how is going your production.
Okay, and finally, we want to give to the audience general conclusions of the AFF 4.0, and we want to highlight the following points. A process optimization methodology has been developed where the data is an essential part of and therefore multiple tools have been developed to deal with the process data at different levels, from the acquisition to the prescription, through the monitoring of the key parameters. All this considering that the tools are aimed at providing decision-making support for process experts. In other words, in this methodology, the expert is the key element that provides domain knowledge, and therefore has the last word when updating the process. The automation or closed-loop approach of a prescriptive approach methodology using artificial intelligence in an industrial environment is very challenging, and this will be addressed in the future in the project or in other projects.
Thank you very much. And now, as it was said, I would like to ask you both to give us the real-time presentation of the platform. So now I will give the presenter for Joseba.
Okay. So first of all, I want to show you just a quick demo regarding to another kind of industry that we work with. This is a steel making demo. This dashboard is a demo of a recoiler. It's a machine that is used to using in steel making. This is real-time or descriptive analytics dashboard. And as you see, this is a live demo. We are simulating a creation of different coils of steel, and the different kind of information that you can see here, the different KPIs that are regarded to steel making, machine states, and the length of the coil that has been processed for this moment. Also, regarding with this kind of visualization of steel making, this one is a demo of as I show you of a monitoring of OEE. Here, this is a more diagnostical visualization tool where we can use different context data as filters. As you can see now, we are filtering just by the line of the production lines that we want to see, but also I can filter by the material and the shift of the day, and it's going to show us the data regarding only with these filters that I'm using. So also I can see index information overlapped to different parts of the visualization. And regarding to the OEE, one of the things that is more important in production are stops and the reason of the stops. So this is a visualization of synthesizing, trying to synthesize the stops using different kind of visualization of the stops that we can have in a steel production. And also here we have the filters, the intelligent filters to apply to the different charts that we are using. This kind of chart that can give us the different percentages of the stops groups and the in-depth definition of the stops. Here, this one is regarded to the time and occurrences of the different stops, and we can filter the not target different stops like this one, and just focus in the most important kind of a group of stops that we want to analyze. And now I'm going to change to the demo of the Cemento Rossi, or the visualization of Cemento Rossi, that are the ones that I show you later. This first one is just a visualization of raw data. As I told you, when we import raw data, is not very useful as information. So as you can see here, with a lot of variables, it's quite complicated to take the information out of this panel. We are watching the mean value of different variables of the process in 7 days. The resolution that we have is 1 hour per point. So if I just focus in one of it and go in depth to analyze just one part of the process like this, I can go in depth, and as you see, dynamically the mean value is changing over time. So now I'm seeing the mean value of 6 hours. And if I go deeper, I go to the last step, that is the mean value of 1 hour. That is just one. We have the resolution of 1.4 or 1 hour, so this is like real data. Okay. Then the second dashboard that I want to show you is the one that we have seen in the presentation. This is, as you see, more complex, but also it gives us more information, or more treated information about the process. Is the same values that we have seen in the past dashboard of raw data. This is the same data, but we have treated or prepared to show more human readable information. And also we have do some calculation regarding to the ratio of the energy efficiency of the production. So we have the top part, the KPIs of the dosification, of the production of one part of the cement industry, the load of the oven, some kind of technical information. But the important thing that we have to follow or monitor is this ratio that has to be more or less near to 22. And here with this kind of box, we only can just show the value and the color of the state of the value, but also we can chart it in this kind of visualization. And then again, we can just go in deep and see what happened in this information with this moment of the process. And finally, the last visualization that I want to show you is how we integrate the optimization objective model results that TECNALIA is calculating with the optimization. This visualization is just to show on the past the results of the training model. Here we have the real data of the KPI that I told you that is the scope of the optimization model, and in red the results or the predictions that the different models have done in different training models that TECNALIA have done. But this is just to show you different kind of visualization data. And now I'm going to pass the control to Fernando. Okay, I think you have the control to show you he's going to show you the visual integration of the optimizer inside the manufacturing analytics tool.
Okay, first I want to say that when we are here, as Joseba said, we have developed some models to have the correlation between the process parameters with the KPIs and some constraints. So we have here the objective of this optimization is to optimize the efficiency of the process, and the tool will provide the optimal parameters for the set points, so the result for these variables. But also we need to define some constraints in the process. So for that we have built another models to predict or have a measure of the quality or the performance of some equipments in the process. So here when we have these models, we can integrate very easily in the tool. As I said, it's very flexible and it's a general tool. And so here the process expert is managing the variables, their process variables. So here the expert can modify the ranges of the variables, but also the process constraint ranges in order to have a different scenario in the process, depending on the requirements right now in the process. So here the process expert can change a range in the process variable, and also here in the constraints. But also another thing the user can do is to fix a variable. For example, here this temperature of the separator, the user has fixed to a value because in this scenario is a requirement for it. So in this moment we can launch the optimization, and we can see here the result the user can have. So we have here different optimization solutions. So we can see how each variable move in the solution space, but also we can have here a detail on each solution to see how each variable change in the solution. And then we have here a detail on the specific values we have to set in the process in this solution. And that's all from our side. I think we finished with the demo.
Okay, thank you very much. And now I think we can go to the question and answer. So we have some questions to the panelists. The first one is to Fernando. Is AFF methodology applicable for any industrial process?
Okay. All the developments in AFF 4.0 have been implemented with a general view, as I said. So the replicability and the flexibility of the tools is complete, taking into account that the tool, what the user manages is completely familiar. So he or she can manage the variables and KPIs. So we can implement multiple industrial cases, and we have to take into account that some requirements are needed, as to have the data, we need to be well defined the optimization part with the KPIs and the restrictions. But as I said, we can manage a high range of industrial cases with our tools.
Okay, thank you. So now we have another question, even two questions to Mayalen Murua. So Mayalen, can you optimize the process to minimize the slack? And the second question is, what are the next steps in soft sensors development?
Okay, yeah, I think both questions are a little bit related. So, because the next step in after developing a subsensor would be to optimize. As Fernando explained, the predictive and the prescriptive analysis, the subsensor is a step in the predictive analysis. So we can do something in the prescriptive analysis by optimizing the generation of the slack to be minimum, and it will be developed using the model that we have built by the subsensor. So that's a work that we are doing. It's a work on progress. We are trying to minimize the generated slack.
Okay, thank you very much. And now the last question, which is for, I think both Fernando or Joseba can answer. What changes needs to be done in factory to implement the AFF technology?
Okay, so for the data acquisition and data management, I think that the changes are minimal, because nowadays we have these edge devices that I told you that can connect to any kind of industrial devices or industrial machines. The only requirement is that this industrial machine has to have connectivity, but this nowadays is one of the things that more or less all of the machines that have integrated by default, such I told you, Modbus TCP or OPC UA communication protocols. So with these edge devices, we can extract information from any kind of industrial devices. One of the good things that you can do, or that the transformation that is going to be more or less a requirement, is not specifically needed, but is very recommended, is to have a segmentation of the IT and OT networks because of regarding to cybersecurity. But other than that, the changes needed are very few. all the exploitation is going to be made in IT layer. So this is a fast deployment and a fast way to start working with minimal data, and then keep growing. We have more needs of taking more information and exploiting in different kind of dashboards or with artificial intelligence models.
Thank you. Yes, I think the more simple is the implementation. I think it's the more interesting for the potential customer. So as this was the last question, now I would like to also inform the attendees that both TECNALIA and MSI staff will be present during the BIEMH and BeDigital events in Bilbao, which will take place on 13th and 17th of June this year. There will be an MSI stands and the presentation also given by Joseba Egia. So if maybe you're thinking about participation in these events and there are some more questions to our panelists, it's a good opportunity to meet them directly in this event. I would like to thanks to all of the panelists for their valuable presentations, and to all the attendees for participating in this event. This was the last out of our 3 webinars, and you can still follow our project in the project's website and social media. Soon the video recording will be published also, so you will be able to see it again. Thank you very much, and have a nice day. Goodbye.
Thank you. Bye bye.
Thank you. Bye bye.
Thank you. Bye.